In today's video on the topic of materials at Physics A level, we're going to look at Hooke's law and springs, stress and strain, and Young's modulus and density. So to start off, if I was to combine two springs together, which arrangement would have a greater extension? To understand how to answer that question, we need to recap Hooke's law quickly. So Hooke's law states that if I was to apply a force to an elastic object, the force applied to the elastic object would be directly proportional to its extension. Now this applies only up to a limit of proportionality. We'll look at later some materials that don't obey this after a certain point. So that's Hooke's law. If we're looking at it in symbol form, we say force is proportional to delta L, or change in L, and the constant of proportionality we call the spring constant, sometimes called the elastic constant, which has the units of newtons per meter, or nm to the -1. So if you were to plot a graph, you might remember this practical, you might have done it at A level as well. You have the change in length and force. If I was to measure the gradient of force divided by change in length, that gives me the spring constant. It should be a nice straight line going through the origin to show that the gradient is constant. Let's then let's have a look at these different arrangement of springs and see if we can figure out which one has a greater extension. Now all the springs here have the same spring constant K, and both arrangements have the same force acting downwards. So if I was to work out the extension, I need to know about the force. Now for our first arrangement next to each other, the force is split evenly between the two springs, meaning each one experiences F/2. So to work out the extension, the spring constant is the same for both, but the force is going to be lower, meaning there's a lower extension for that arrangement. Talk about them parallel, they both experience the same force because the force is acting downwards on both of them, and both the springs are actually going to extend as well, have a change in length. So that means then you're going to have a greater change in length than there was compared to the arrangement on the left. Now the arrangement on the left is called the parallel arrangement because the springs are parallel to each other, and to work out the overall spring constant you just need to simply add together the spring constant of the individual springs. Next, for the one in series, it's a little bit more complicated, and I'll show you how we can go about working out what the spring constant overall is going to be. So if I was to add together for our series arrangement the individual changes in length, I'm going to have individual forces divided by spring constants. But if the force is the same throughout all of them, I can replace the F's with a 1, so 1 over each one. So that means then for my overall spring constant, I can do 1 over the spring constant equals 1 divided by spring constant 1 plus 1 divided by spring constant 2, etc., which is sometimes known as a reciprocal addition, and it comes up with electrical circuits as well. So the idea is if I've got the same value for spring constant, which is by far the more likely scenario you'll be asked about at A level, if I have two springs, I'm going to have half the spring constant, whereas for in parallel, I'm going to have double the spring constant. Okay, let's have a look at force extension graphs then. So for Hooke's law, they are directly proportional, and that leads us to an equation for the energy stored in a spring, which is the area under this graph, which is half force times extension. It's a half because it's a triangle, so half base times height. But that rule applies for any object which you're applying force to, which is elastic. So substituting in Hooke's law to that, we can come up with another expression. I can replace F with K times by delta L, and that gives me half times by K spring constant times by extension squared, which is an alternative way of calculating the energy stored in a spring. Now, force extension graphs look a little bit different for materials that don't follow Hooke's law, or don't have a constant elastic constant or spring constant. For example, a polythene bag like the one you go shopping with. If you were to attach some weights on the end of it, it doesn't extend in a linear fashion. You'll get a graph that looks a bit like this. I've got force on the bottom and extension on the y-axis this time. Initially, I'm going to have a lot of force to make a little bit of extension. Then, all of a sudden, I'm going to have a lot of extension, even though I'm not adding much extra force. So, spring would be directly proportional. Add up like a polythene bag would be this blue line, the shape of it here, and it could have, for example, a rubber band as well, which another object which doesn't obey Hooke's law has a non-constant spring constant or elastic constant. So for our polythene bag, I've got a low force initially, then a large extension, then at the end I've got a large extension, even though there is not much force being added overall, which kind of makes sense if you imagine, like, you know, at one point when you're carrying your strop in, you put a lot of extra stuff in, it doesn't stretch much, then you put a bit more in, suddenly it stretches a lot. Now, there's a difference in our force extension graphs if I'm loading or unloading a material. So a loading graph, like this one here for an elastic band, and if I unload the weights from it, there's usually a slight gap between the graphs. Now, if I'm talking about the loading graph, the energy that that's stored in the rubber band would be the area underneath it, and if I unload it, that is the energy released as I'm unloading the rubber band. So there is a difference between those two energies, and the gap between those two graphs is the energy that's dissipated to the surroundings as heat. If you stretch an elastic band and unstretch it lots of times, you'll notice it gets hot. So this energy is dissipated to surrounding air as thermal energy. So what about objects then that aren't elastic, like our polythene bag? Once you stretch it past a certain point, what does the graph look like? So once we stretch our, let's say, a polythene bag past a certain point, if you start unloading it, it's not necessarily going to go back to its original shape. So this indicates there's a non-elastic material. It's not elastic, meaning it's not going to go back to the origin or back to its original length or shape. And the name for that is plastic. That's a plastic material, which we'll come on to a little bit later. Okay, so as we mentioned with our Hooke's law definition, every material will have a limit of proportionality. It might not be a great deal of force needed to surpass that, but our spring, for example, would be somewhere towards the end of the straight line. The rubber band polythene, there is a straight line for a small amount, therefore meaning a base Hooke's law, and those two things are proportional. Next, let's move on to stress and strain. So the idea behind stress and strain are they essentially give us more information about the material, because not all materials are springs or are elastic, and actually they don't factor in things like the cross-sectional area or the length of the material. So let's define stress first of all. So stress, which is given by this small case sigma, is force divided by unit area, or tensile force divided by the cross-sectional area of the material. So the units, forces in newtons, areas in meters, so therefore it's newtons per meter, but could also be written as pascals, so PA, alternative unit, which is identical to newtons per meter squared. Strain, we're going to use the symbol epsilon for, is the change in length, or delta L, divided by the original length. So it's extension divided by original length, which, if you look at the units, we've got meters divided by meters, so therefore strain is just a ratio. So it can be given as percentage strain sometimes. It's usually just a number, which is the ratio extension divided by original length. So let's talk about Young modulus of a material then. So Young modulus is given by the stress divided by the strain. So therefore we are going to have F over A divided by delta L over L, which looks very messy. So let's rearrange it slightly. So I've got F stays on the top, A goes to the bottom, delta L stays on the bottom, and if you're dividing by something on the denominator, you can put it at the top. So we've got FL divided by A times by extension. You're not going to have that given to you in an AQA exam board, so make sure you know how to derive it. And Young modulus is got the same units as stress, which is newtons per meter squared or pascals. It's worth noting that cross-sectional area is normally a very small value because 1 meter squared is quite a big material. So often you'll find Young modulus and stress given in megapascals, gigapascals. They're usually quite a large unit. So let's have a look at Young modulus graph. So one of the key parts of this topic is a stress-strain graph, which you can work out the Young modulus from. So I'm going to put strain on my x-axis, and I'm going to put stress on my y-axis. And this graph is going to be for a ductile material or a wire. And let's see what it looks like. Now, there is a required practical for this particular graph as well, usually stretching a metal wire and seeing what the Young modulus is, which you stretch usually using a vernier scale, so you can measure very small extensions because it won't stretch by that much. So let's say we've got our wire stretching. There's going to be a significant part of the stretch is going to be have a constant gradient, or it's going to have a direct proportion between stress and strain. So therefore, when these two things are proportional, we can measure the Young modulus only when it's a straight line, because that shows it's got a constant Young modulus at that point. So an alternative way of doing it is for a force extension graph, which is essentially what you're doing. You're applying a force measuring the extension, and we can use the gradient of that to help us find Young modulus. So using the equation I derived a couple of minutes ago, Young's modulus equals force times length over extension times area. So if I kind of separate out the force divided by extension, and I rearrange for the Young modulus E, what I'm going to get is Young modulus equals the gradient of the line times by the length divided by the area, which, because area and length are constant, is a kind of easier way of doing it rather than plotting a stress strain graph. So let's have a look then for our stress strain graphs. Now these can be quite tricky, and one thing to remember is they're not necessarily chronological. It's not a time on the x-axis, so these things can happen at at different times. You can take weights on, add them on to kind of change the stress. So after we get past this point here, which is our limit of proportionality, so that's where we can measure stress and strain up to, we'll find our next point is called our elastic limit. So our elastic limit is where it exhibits elastic behavior, and after that would exhibit plastic behavior. Now these 2 points can be the same. You'll find them different on most graphs, just to distinguish between them. After that point, we have what's called the yield region, or sometimes called the yield points. Okay, so at that point, it's defined by, even if I'm decreasing the stress, the strain is increasing. So I have high amount of strain for very little or no stress added. Now the top of the graph, the maximum stress reached, is called the ultimate tensile stress, or UTS, and as the name suggests, that is the kind of highest possible stress a material can withstand. It doesn't have to be the same point as the fracture or the breaking point. Sometimes it is, but you can take weights off so the stress is decreasing before it then fractures once it goes past a certain strain. So this region here can also be termed a plastic deformation region, so that's because its material is not going to return to its original shape. So once it's past the elastic point, that's the kind of plastic region as well. So quite a confusing graph, and make sure you know the key points, how to label it and the shape of it, and bear in mind, as I mentioned before, this is for a wire or a ductile material, not for all materials. Most materials are not as complex a shape as this, but obviously most metals can be drawn into wires, and so therefore it's quite a common thing we're going to talk about. So let's compare some other materials then. So we've got our wire from the graph above, so that's ductile, meaning it can be drawn into any shape. In particular, it can be drawn into a wire, so that's only for metals. And we've got other materials, so we could talk about things that are quite like brittle, and things that are quite a lot of strain. So we could talk about glass as an example of something that's quite brittle. So the idea there is it shows very little strain before fracture or before breaking, indicated by the mostly straight line, then a tiny bit of strain before it breaks. We could also talk about materials and their strength, or whether they're strong. So they would have a high gradient on these graphs, or a high amount of stress needed for a small amount of strain. So not necessarily a metal, could be metal, but the higher the gradient, the stronger the material is, just like with our force extension graphs. Okay, to finish off the topic of materials, we're going to talk about density, which comes up at GCSE, obviously, so you should be relatively familiar with this. So let's talk first about how you'd measure the density for different objects in 3D. So if you're talking about a object like a sphere or a cylinder, you wouldn't need to memorize it because it's on your equation sheet, but you need to be able to apply the equations for volume of these objects. So they could just give you the radius of the sphere and ask you to work out the density if you know the mass. A cube is the easiest. You'd find, obviously, that's the length multiplied by itself 3 times. So to measure the mass of an object, we're going to use a balance to find that out. The difficulty comes if I've got an irregular object, such as like a screw or any shape that's not one of the above really. How do I find the volume of it? So we have what's called a Eureka can, or a displacement can, which has a spout with a measuring cylinder underneath it. So if I lower an object into it filled with water, it will displace a certain volume of water. Now the volume displaced will be equal to the volume of the object. This is after Archimedes kind of discovered this way back thousands of years ago, and was able to figure out, well, that I can use that to measure the density of different objects. So tricky density questions can come up if you've got alloys or things with 2 different materials in them, like this example where I've got copper and tin mixed together. So what I'd have to do to work out the overall density or the overall mass is to work out the volume separately, and then work out the masses separately, and then use that to work out the overall mass. So to work out the volume of the copper, I do the mass of the copper divided by density. And then essentially kind of add them together. So lots of exam questions on this. Make sure you practice. They can be quite tricky to interpret. So I hope you found that helpful. And please watch some of my other videos for more Year 12 content.